What's up guys, it's me Sir Ernest, and today we're going to talk about Newton's laws of motion. Okay, so we already know from our university physics class that there are three laws of motion formulated by Isaac Newton. Now these are the law of inertia, the law of acceleration, and the law of interaction. So the first law basically states that a body remains at rest or in uniform motion unless acted upon by a force. In equation form, this Newton's law, or the first law of motion, states that the net force acting on a particle, so let's say if you have a particle of mass m, there are, let's say, 1, 2, and 3 forces. Now the net force acting on the particle is just the sum of all the forces acting on this particle m. Now, first law states that the net force acting on the particle is equal to 0. As a consequence, the particle is either at rest or in uniform motion. So when we say uniform motion, that means the particle is moving in a straight line with a constant speed. Now, the first law conveys the physical meaning of what we call the zero force. So that means if the particle or a body will remain at rest or in uniform motion if it is subject to no force whatsoever. So you say no force, that means we're talking about no net force. And if that's the case, a body moving in this manner is referred to as a free body. Or sometimes we call this free particle. Now the question of the frame of reference with respect to which the uniform motion is to be measured will be discussed later. Now, the second law of motion, on the other hand, states that a body acted upon by a force moves in such a manner that the time rate of change of momentum equals the force. But originally, this is said to be the net force acting on the particle is just equal to the mass times the acceleration. Here we assume that the particle's mass remain unchanged. So that means the mass of the particle is constant. Now, this equation tells us that if the force exerted on a particle is non-zero, unlike in the first law, the particle, assuming that the mass remain constant, will accelerate. Now, together with Newton's first law, Newton's second law operationally defines what a force is. And this force dictates also the acceleration of the particle, because in this case, this equation generally tells us that forces causes objects to accelerate. So when we say acceleration, that means the velocity change. And that can happen by undergoing several things. The particle can either speed up, slow down, or change in direction. So any of those two, or of those three cases, or a combination of which, is said to be that the particle accelerates. And when the object, or when an object accelerates, that means a net force acts on it. And the direction of the particle's acceleration caused by the force is the same as the direction of the force that causes the motion. So for example, if this is your particle of mass m, if the force is in this direction, the resulting acceleration will also be in that direction. Mathematically, that is supported by our discussion before, that when a vector is multiplied with a scalar, the direction of the resulting vector will follow the direction of the original vector. So in this case, that's your acceleration. Now, the third law of motion is not really a general law of nature. The third law of motion states that if two bodies exert forces on each other, so for example, you have again one mass and then the second mass, and let's say these two objects exert forces on each other. So let's say, for example, M1 pulls M2 with a force F2. This particle will exert an equal force in terms of magnitude, but the direction of that force would be opposite the force that acts on it. In our illustration here, that would be in this direction. So this is the force exerted by 2 on 1. As I mentioned earlier, Newton's third law is not really a general for a law of nature, in a sense that it is applied to all, to everything. However, the law does apply when the force exerted by one particle on another particle is directed along the line connecting the two particles. Okay? So for example, or in this case, if F1 and F2, these two forces, or this interaction between this M1 and M2, follows Newton's third law if the two forces are acting along the same line. So if this is the case, the force exerted by M2 on M1 would be equal in magnitude but opposite in direction as the force exerted by 1 on 2. Now, as I mentioned earlier, this law applies to forces wherein those two forces are directed along the line connecting them, and we call these forces central forces. Now, the force of interaction is either repulsive or attractive depending on the nature of the force. So, for example, if the force is gravitational in nature, these two forces will be attractive. However, if these two forces are electrostatic in nature, for example, the two forces may be attractive or repulsive depending on the sign of the charges of the two particles. Now, any force that depends on velocities, for example, gravitation, magnetism, or magnetic forces, these forces may not apply, or the third law of motion may not apply, because the velocity-dependent forces are characteristic of interactions that propagate with a finite velocity. Therefore, the force between moving charges, for example, does not obey the third law, because the force propagates with the velocity of light. Even the gravitational force between two moving objects is velocity dependent, but the effect is so small and it is difficult to detect. Now we're going to discuss more about Newton's third law in the next video, wherein together with Newton's second law, we are going to define or express the second law, third law of motion in terms of the physical quantity called the linear momentum. Okay, so for now, that's a brief introduction of Newton's laws of motion, and in the next video, we're going to extend this discussion in terms of the linear momentum. So that's all for now. Thank you for watching. I hope you learned something today, and I'll see you guys in the next video. Bye bye.